Hi folks, so we're back for some more differential data flow programming, working on a project that we started last episode where we were trying to build a Minesweeper implementation in differential data flow. And if you were there for the last episode, we got a bit of a skeleton up and running after a few hiccups. And I thought I'd sort of talk through it again, and maybe we'll do a little bit of cleanup. I've actually already done a little bit of cleanup. I feel a little bad, and I'll talk you through sorts of things that I did. We'll start to draw some pictures on the screen, and what I actually wanted to do was to play around a little bit with this cursive package that I've played around very superficially with, and it makes nice little pictures show up. It's like a cursive library for the terminal, and so you can draw some pictures, but like, you know, text, GUI looking stuff in the text, and maybe we can actually draw our Minesweeper output there and have it look a bit more, I don't know, like an actual interactive bit of program. The cursive stuff allows you to handle like clicks, for example, so we can have people potentially, if we're good, select and unselect locations, sort of place down mine-like things, and we'll see what happens. So just to talk you through where we were before, we are building a little Minesweeper implementation. I've re-rigged things so that the program itself takes two inputs, a numerator and a denominator, that control the density of mines throughout the world. Basically, the world is this sort of unbounded XY grid, or this pairs of I64s. So it just goes off indefinitely in each direction out to, pretty big. And some fraction of the locations there contain mines, and that's stimulating. And you get to specify that as some arguments up here. We spin up a little computation, timely data flow computation, thusly. And we're going to, in the example at the moment at least, give each of the workers a copy of a multiple producer single consumer queue that they can use to send their outputs back to the main thread here, so that it can draw pictures for us on the in the output. Essentially, we'll see in just a moment. And some stuff goes on. What each worker is going to do is create a data flow, and that data flow is going to start from a bunch of inputs, these guesses here that we sort of initialize in this new collection call. The guesses are just going to be XY locations. These are places that you've clicked, if you will, in your Minesweeper game, and you've sort of thrown your lot to see what is on the other side of that click. Is it mines? Is it hopefully not, and it's instead a number that tells you how many of the immediately adjacent squares of the 8 adjacent squares have mines in them, from which you might use your brain and think about some way to proceed. Now, starting from that, like we could in principle, and we did previously, just go and count the number of nearby locations that have a mine. And we'll see how that's done as we go along. But we built up a bit of logic that will take those guesses and iteratively unfold them. So for the set of guesses, if any of them happen to have count 0, meaning there's no mines anywhere adjacent to them, that's great. That means that we should more or less just go and include all of the 8 neighbors as additional guesses. We know that they're all safe. Might as well expand them out. And indeed, this is what the Minesweeper game does when you play it, just to make your life a bit easier. When you click on an empty region, it sort of opens up all of the related surrounding space. So we want to write that. And the way it works is that we take guesses and we iterate through it, where in each of the rounds of iteration, we take the current set of guessed locations. And we go through, we start by forming the, put some comments in here. So we're going to start by forming the count of the neighbor mines for each of the guesses. So we're going to take each of our XY pairs, and we're going to wander around through each of the neighbors. This actually includes the location itself. We'll have to figure out if that's problematic or not later on. But it uses whatever logic we've cooked up, and it's this right here, in fact, to determine if a mine is present at a location. So we've decided to say, well, take the pair XP, YP, hash it up, and use the denominator and the numerator to try to determine, roughly the right fraction if this location has a mine in it or not. And we're gonna count up the number of immediately adjacent neighbors that have mines in them, starting from 1 for some reason. We'll get to that. And we produce that as our output. So what explode does is lets you specify a record to produce and a count to produce it with. So instead of, this is more useful if this was like 1 million or something. You don't want to actually produce 1 million copies of XY. You just want to tell the underlying system, please, do plus 1 million to its count. But we're just saying, take each location that's a guess. Here's a count that started at 1 and went up. We're going to hit this now with the actual differential Dataflow count operator that will essentially turn this into data that is x, y, and then the sum. I guess the count is what we're calling it here. And we subtract 1 from it. We subtract 1 essentially to undo what we did here. This is important because we do want to see for each of these guesses if it is a 0, right? We don't want it to vanish if there's nothing, if there are no mines near it. We want it to still exist and proudly announce I'm a 0. So we start at 1 and do a count, and then change the data back down to 0 afterwards. And so that's good. This tells us what are the counts for each of our guesses. And to continue the iteration, we're then going to take the 0 counts and expand or unfold. I guess I've been calling it unfold their neighbors. So for each count that has a value of 0, we're going to grab the x's and the y's and enumerate all of their neighbors and enumerate all of our current, add in our current iterates as well, and hit that with a distinct and say, great, next time around, we're going to keep all of our previous guesses, but we're also going to expand out the neighborhood around anyone who had a count of 0. And that's it. That's the iteration. So that will proceed, as long as there continue to be changes. And the way we've written up the logic, this is essentially as long as we continue to grow the set of guesses that we're guessing. So yeah, hopefully at some point this stops. We haven't put any a priori bounds on the size other than U64s and their size. Any max bounds on things. So who knows for how long it'll run. I64s. Apologize. Signed integers, not unsigned. We'll run out of memory long before we wrap any digits around. All right. So after this iteration, what we've got coming out of here are a bunch of guesses. So just XY locations, and we hit them with a consolidate because if things have been added or removed for that this happens for various reasons, consolidate cleans that up. If you were watching the previous video, we were mystified why we were seeing some numbers which had a diff of 0 coming out here, and it turns out that's just because we were using a old version of differential Dataflow. Actually, let's go fix that right now. I went and tested this in my local copy of the repo, and the problem is we're running off to bother. I have to remember how to. Sorry, I'm just gonna go steal this again from somewhere. For whatever reason, my brain is not brilliant when it comes to remembering exactly how to write certain things. So we want to steal this notation here. Great. So differential Dataflow is going to be differential Dataflow, and timely Dataflow is going to be like so. And these are now much more current. I apologize for how out of date the most recent cargo release is. Sorry, crates release as compared to the head of master. All right, so that's largely sorted. And then because we haven't really written this particularly well yet, these guesses come out, but we don't want to just announce where did you guess or where did we unfold your guessing to. We actually want those counts again. So we copied and pasted all this logic here, and we're gonna try to fix this up today. Remove all this redundancy, but this will get us back our counts for all of our guesses. And then we grab everything that we've seen, and we sort of drop it into the send side of that MPSC channel that we had created, which is going to be useful for collecting all the results outside the computation. And we start off just by dropping in a single sort of boring 0, 0 Any point should be largely the same wherever we start from, because it's just in the middle of space, essentially. It might be more interesting to start somewhere else, actually, because one thing we'll see as we play around with this a bit is that the hash that we're using is FNV, and it's not a cryptographically strong hash, and we'll see some weird patterns show up. But then we grab all that data, and we take all the outputs that we've received, and we stash them in a hash map. I'd previously stashed them in a vector in a really janky way, but basically we just want to wander through, and for every pair of coordinates that we see, x and y, put that in a hash map with whatever the count was that we got. And then this is my sort of lame attempt to try to draw a picture, basically. So we're going to take a y value going from -15 to 15, and x -25 to 25. And if we find some of each of those locations, we'll print out a thing. And if we don't find anything, we'll print out an empty space. And this is basically trying to draw a picture once. It's not especially good. But let's see what happens here. Oh no, I've revealed some of the things that happen. Well, I suppose one thing that happens, we get to wait a while while it rebuilds in release mode. Release isn't strictly necessary. So I was doing release because I found a let's do 1 and 10. I found a case where it was sort of sprawling out and using epic amounts of memory because it grew in unboundedly, and I wanted to see how fast it could grow, which it got up to like a few gigs of memory in just a few seconds. So it's I'm very proud that it ran out of control quite that quickly. So this is all of the observed nonsense up here. I have no idea what's going on with this crazy. Oh, that's right. Sorry. If we don't specify a starting time for our timestamp, we use the min value, and the timestamp I said was int32, and that has a min value of this nonsense. But we've got a picture down here, right? This stuff is our starting from, I don't want to guess, maybe right there in the middle, 0, 0, and sort of spilling outwards. We've set it up so that 1 out of every 10 locations, roughly, is a mine, and I guess that's a density where it grows out a little bit and doesn't run totally wild, but does expand for some amount of time. And actually, I've not looked into the sort of the math behind Minesweeper and under what circumstances does it grow unboundedly or not. I'm sure someone else has looked into this, but I can't tell you what the answer is at the moment. So this is sort of nice. In the previous episode, we only had x's being drawn here because I couldn't figure out how to produce the actual numbers, because I think I was trying to add numbers to the character for 0, and it turns out Rust actually, if you look over here on the left, has wonderful facilities just to print numbers, and I'm not sure why it wasn't occurring to me at the time, but here we go. So this is an example of what we produced before, and it's it's primitive. It sort of shows us that a thing was happening, though. There's some other things that you can do. So here's if we do 1 out of every 9 locations as a mine, we have this 2 in the middle, and we don't actually expand anything because it's just a 2. The rule doesn't let us expand. But if this is the same as what it was before, 8 is a bit interesting. So 8, you might look at this and say, wow, that's a pretty terrible mine distribution. 1 out of every 8 locations, and it's not very random. And indeed, I think this is essentially the fact that we're using FNV, and that 1 out of 8 locations, 8's a power of 2, and FNV is essentially sort of shifts some bits around and folds them in and XORs some things together, or adds them, I'm not sure. But you could totally imagine that as X and Y move diagonally, they have a bunch of bits that align, like their lower order bits align, and so quite plausibly some things sort of hold invariant. And if you look at what's going on here, this basically grows unboundedly out until it crosses out of the first byte and into the second byte. So counts up, X's and Y's count up to about 256, and then it just magically stops. So it doesn't go on forever. It does actually terminate when something changes about the FNV computation on these fairly similar looking bytes. All right, so that's roughly where we are at the moment. We can draw some pictures there. I wanted to do a few things. I wanted to try to clean stuff up a little bit. I wanted to show you maybe first, before we clean anything up. This is a fairly short bit of this cursive stuff that I sort of, I borrowed out of an example that they have, modified a bit to look a bit like Sudoku, and I just wanted to show you what that looks like. Just because, it's I think it's sort of cool. So, this is now the cursive project over on the left. Let's see if I can, we've rigged it up. So far it's super easy to use. I've rigged it up so if you press Q, it quits out. Otherwise, it adds this layer, which you're looking at now, this big panel, that is whatever struct you want. It's got some state. I put some random stuff in there. I was basically going to make it be a Sudoku board. And you just implement some stuff that says, what should I do when I draw, when I'm asked to draw myself? And how should I respond to various events? So I've got it rigged so that if you run around double clicking on things, oh, sorry, not for whatever reason the VS Code thing doesn't really like this. So let's projects Minesweeper. Oh, there we go. It only actually does a thing if you double click on an actual Sudoku location, and there's some like gaps between. So like I've tried to actually build this so that it would look like Sudoku would look. And if you miss any of the locations, nothing gets presented when you double click. But you can double click again, and it unsets it, and that's it. It's not super complicated, but it seems entirely appropriate for Minesweeper. And that stuff there was just this much code, essentially. Your state. What do you do on various mouse clicks? In this case, you could respond to lots of things. I just wrote the mouse clicking or mouse releasing even. And based on that state, what do you actually draw? So we're gonna probably try to exfiltrate some state from this Minesweeper example, live state, and draw it using an example largely like we've got over there. And it'll be a little different. It'll be numbers hopefully that tell you the things that look a bit more like all these mine things that we've been drawing, but maybe in a way that we can click on them and sort of undo things and redo things and have it expand or not. Yeah. So if we had this sort of thing in that sort of framework, but one where we can, well, double clicking doesn't make a lot of sense here, I guess, but double click on some of these locations to activate or deactivate them and maybe make it look a bit more like an interactive program. So that's on the menu. Another thing that I want to do is just try to tidy up the code here a little bit. We have this redundancy between our logic for figuring out how many mines are adjacent to someone here, and it's exactly the same thing up here. And the reason why is we're doing this iterative computation that starts from some guesses, goes around the loop, and what we want to get out of it is the guesses and their counts. And that's a little bit awkward for iteration because we have a different type that comes out than goes in. So I'm going to try to write up a iterative computation where we iterate in a nice sane way, but we're able to export different data than we took as input. I'll show you what that looks like just a bit. Maybe right now actually, because I don't think there's anything else that I really wanted to tidy. So so iteration is a specific instance of a timely data flow scope. So we're building a data flow here, right? And when we build the data flow, this makes a canvas for us to put data flow operators into. And every operator in that data flow has some timestamp. In this case, it's in 32s. But in all of these canvases, we can make sort of sub-scopes, sub-nested canvases that can have additional timestamps. And that's what's going on with Iterate. It's saying, you know what, let's take a break from this main data flow then. Let's make a nested data flow within which we'll start building up some operators that have an additional timestamp, and it's going to be the round of iteration. And we wire things up in a fairly particular way to try to make life easy for you when you call Iterate. But we can also just unpack a bunch of what's going on in Iterate. And let's actually wander over and take a look at what Iterate does. This code is not super complicated, but it is definitely subtle. So we need to be a little bit careful. So this is the iterate implementation for collection, which is what we've been using so far. So collection is just a timely data flow stream that has some diffs in it, some pluses and minuses that talk about how data change. And when we look at the iterate implementation, the logic is essentially that we create a new scope, right? This is where we're creating our new timely data flow scope. We're going to call it, we'll give it a name, which is, I suppose, iterate, and it's defined by a closure that says, if you had a handle to the scope, what would you do? So the scope is something that allows you to build operators and create edges and stuff like that. And we don't do very much, actually. Like it's just 4 lines. There's a lot baked into these lines, and we're going to just borrow a lot of these as well. But we create a variable. A variable is a differential data flow construct that says, I'm essentially a stream that you can use right now and define my contents later on. Right? So we can start using it right now, and once we've figured out what we want it to be, possibly in terms of itself, we can then bind its definition, and that will create a bit of cyclic data flow, where as data flow back around to the source of the variable from its definition back to its source, the iteration counter ticks once, basically. That corresponds to one time around the loop. So we're going to say, hey, great, let's create this new variable that's initially the collection itself. We are going to run whatever logic you give us. So iterate, if you recall, is defined by some closure that says, what do we do with each of the iterates? So we're just going to run that. We're going to say, like, if you gave us some contents, some collection contents, do whatever you need to do, get us a result out, and then we'll just bind that definition back to the variable. And this creates a loop back that sort of says, we potentially used variable in its own definition, but that's fine. It just sets up a little bit of feedback here. And then to return a result, we're just going to take that result that we had, and .leave, which pops it back out of this nested scope and says, you probably wanted that thing that was iterating, right? And that's going to be the thing that changes a little bit in our computation. We don't actually want the thing that was iterating. We want something sort of halfway up the computation. So let's just steal this. And what we're going to do is something very similar, basically. We're going to drop this over here. There's no more selfs, so we're going to take guesses. So we're going to manually assemble an iterative data flow. And we give it a name. I'm not really sure, unfold guesses. This is largely irrelevant unless you're looking at the diagnostic information that comes out of timely data flow, and it needs to identify each of its operators. And you can sort of see, oh, that's that data flow. We are still going to create a variable, and it's still going to be something like guesses entering into the subgraph. So we still want to start out all of our guessing essentially with some non-empty collection here. This stuff over here, don't sweat it too much. You can look into this, but essentially we need to tell timely data flow and differential data flow how to increment timestamps. So it doesn't know necessarily what it should do to these things. We know in our, it's sort of obvious that if we have a new iteration counter, we should probably increment that by 1. It doesn't know that, so we just need to sort of tell it, here's what happens to timestamps as they go back around this variable. All right, so now instead of calling logic, we don't have this logic thing anymore. We are going to steal this stuff here, and we're going to let counts equal variable dot dot all this stuff. So this used to be current. There's just going to be variable now. We've just given it a new name, and we'll make it clear as we let's go around. And this is actually pretty exciting. This is what we're going to want to return out once we reach fixed point. So actually, let's do that right away. So at the very end, whatever we end up doing, we're going to produce counts.leave, which is not the same type as guesses. But we do need to sort of bind this definition somehow. So let's do that. Did I just leave some half-formed comment there? Wow. So we'll create a thing calling it unfold here. Instead of applying logic to variable, getting results, going to do unfold, and we'll set this to be unfold. I happen to like changing the names every time you do one of these things, just so you don't accidentally reuse the thing and screw something up. And what the very important distinction here is that we're gonna return the guesses with counts, as opposed to just the guesses themselves. And we will still consolidate this. And I think we need to give it a name. We used to call it reports. I'm going to violate my rule there and just reuse reports to make life easy. But we are no longer doing this big hunk of iteration here, so let me just delete that. And we no longer need to redo these reports. Actually, we could just call this thing counts, couldn't we? So, right, so we've created this new variable. Let's just make this slightly differently formatted. There. We've created this explicitly constructed sort of Dataflow subgraph where we can set up our own iterative computation using this differential Dataflow variable thing. And we've sort of manually described the computation, set the variable at the end. Hopefully this isn't too complicated. Like it's meant to be that if you've got some exciting mutually recursive setup where like maybe there's a few different variables and they feed into each other, then you can totally just write your things yourself here. Let's see if this checks out. Not quite. All right. Well, let's see. Okay, so we need, this is a good point. All those examples had a bunch of using statements up top. So let's do similar sorts of things. I suppose we can put this down there. This is going to be timely order product, so that product type that we're using to advance things here needs some help also. I suppose, sorry, we could put this down here as well. And current, yeah, we don't have current anymore. We have instead variable. Yeah. We'll also need the timely Dataflow scope trait to be able to call scoped. Cannot infer type. All right. So this is so these subgraphs are allowed to have arbitrary timestamp types as long as they refine the outer timestamp type. And I think we just need to be more explicit. Let's see what do we do over here? That's something. Possibly it's the return type that makes it clear. Oh, I don't know actually. Let's try to be a bit more explicit though. We could, for example, and for the type parameter for t on the associated function scope. So the parameter should be pair of I32, because I32 is what we're using out here, and whatever type we're attempting to use in the interior. Let's see if let's open up the scoped method just to. I'm actually not super familiar with the type signature there myself. So there's a T, an R, and an F. The T is the timestamp type, F is the function, R is the result. So let's see if that passes muster. All right. Yeah, all right. And we've stopped using the iterate trait, which we can go and just sort of sneak out. We don't need that anymore. Great. All right, so this checks out now, and maybe if we run it, hopefully we see a very similar picture. Even odds that it just explodes. No, okay, good. So the same thing happens. This is definitely the picture again, looks like a chicken or something. But we've built this data flow graph over here that is manually assembled and only has this fragment in here once. You might say that, like, well, we've probably netted positive a whole lot of code, but at the same time, if we were to look at the data flow graph, we would see that we're not doing a redundant computation anymore. We're not doing this fragment multiple times. And this, to be honest, this fragment isn't super complicated, so it's not the end of the world. But it felt like a good teachable moment to sort of walk through and say, here's how you build your own iterative data flow graphs. And as soon as you get comfortable with variable, then you should be good to go. Yeah, all right. So great. So we have this set up now where we are running this thing. We can start from various points. We do one step essentially, and we'll want to fix that, of course, to try to do some better stepping. But let's think for a moment now about how we might use this cursive stuff and what this program looks like and how we're going to need to interact with it. So, for example, this main function here sets up a bunch of sort of callbacks and stuff. It's sort of event-driven. As you screw around with the program, it will call various things like redrawing itself and stuff like that. And then we tell it to go off and run. And almost certainly at this point, it sort of steals the main thread, and we shouldn't assume that we can do anything more on it. So my guess is that what we're going to want to do is build up our timely data flow computation, and this will spin off onto multiple different worker threads. Right, so we'll build this up, and roughly here we're gonna probably think about doing one of these cursive computations. So we'll put something in here that will start drawing some stuff on the screen and hopefully steal some appropriate information from this computation. And we're gonna see just how painful that is. There's a few ways that you can do it, and we might end up trying a few of them. We've already seen one of them that's fairly primitive, right? Which is just that if we create a send-receive pair, we can hand the sends off to various workers, and then the receive side of it. Extract is fairly brutal. It says, like, I'll just try to grab everything from there, and I'll wait until it's done. But we could also slowly pull out the results and piece back together the state based on these changes that we see. That might be a sane thing to start with, to be honest, because that involves the fewest funny moving parts. Differential Dataflow also has its own way to share state around in indexed form. That means that you can sort of look at the state that it's keeping, and that can be handy if you don't want to make a second copy of all the state. But let's just start with something that's as simple as possible. So we have cursive already in our cargo.toml. So we sort of just need to make sure that we throw in some of these includes. We'll find out which ones, and steal this sort of stuff here. We are, we'll keep this around because we're going to want to do some similar sorts of stuff, but I think ultimately we don't really want to use any of that. So this is the moment, this simple view where we install something. Probably something based on that receive handle. Something that is going to be able to repeatedly redraw itself, and we'll have to write that. So we can still call it board view. That seems fine. And default is probably not right. Let's do new of recv, and we'll have to scribble down what this function looks like, but that's fine. So I'm just gonna trash all of this. We'll reproduce it. So what's a board view? Could be a bunch of things, right? What we're probably going to do, just in terms of drawing, is have, I'm thinking, a hash map from pairs I64, I64, so these are the XY pairs, to a count, and I think this is probably an isize. We'll have to check to see what we use. Differential Dataflow uses isize by default for its counting things, but we'll be able to check that out. So sorry, this is the state, and we're also going to need to have this recv thing, which is a std sync mpsc receiver of some type, and we'll need to learn what that type is. It's probably honestly, I'm not entirely sure. I think it's going to be some timely event types that we'll need to slog through, and that's going to be annoying. You get to see in these receivers both the data that flow out, that's super nice, but also the progress messages that make it clear to you, hopefully make it clear to you, what should you be expecting to see again in the future. And I think we're largely going to ignore those. We're just going to sort of live update our state, and if it's inconsistent because we haven't gotten all the data out, whatever, we'll just show it to people anyhow, and it should quiesce. But we'll feel a little bad. And we might try to think about better ways to get consistent cuts through this data. All right. So without having written this yet, we'll have to get back to that. Let's just sketch out some of the other stuff we're going to need. So Cursive has this concept of a view. View has a few important methods. Let's just steal the whole implementation here, and we're going to delete a lot of the implementation because a lot of it's not correct for Minesweeper. So what do we need to do in implementing a cursive view? I think my understanding is the only required method is this draw thing. So this is going to redraw the view when asked, and this is essentially from scratch. So system comes and says, hey, draw yourself into this region here, and we're probably just gonna sort of barge through our state here and try to plop those, whatever we have in our state, down into this particular region. And we should have, we might have to look on the internet to find it. We should have in here some properties that tell us just how big it is and stuff like that. We also have this required size thing that we could just bake this in and say, look, it's going to be 70 by 35. So what does this look like? Let's give this a height and a width. No idea what they're supposed to be. Let's say usize. So I anticipate that what we want to do here is wander through for x in 0 dot dot. I think I'm hoping it's 0 based. Well, I guess we'll find out. For x in dot dot width, or y in 0 dot dot height. We're going to look into our little state map, self dot state dot get x comma y. Then we are going to want to fire off whatever's going on over here. We're going to take our account and we're going to just print it out thusly, and we'll have to look into these colors and see if these are sufficiently exciting colors or not. But morally, I think that's what we're going to want to do. And we also have this just trash this, I guess. We also have this onEvent method, which you don't have to implement. We can see what goes on without it. But this is the thing where we get to respond to various mouse events, clicking, for example, on our program. And this is in Sudoku land. I sort of try to figure out which number might you have pressed and put that into the state. But we're not going to do that. If anything, actually, we haven't wired this up yet. But if anything, we should see if we can't send some data back to our computation. And that's going to be, I haven't actually done that in a while, so we'll have to see, again, have another thread feed data off to here. We might need to spin this off into a thread that sort of hangs around and blocks on a queue, or, yeah, I'm not actually, interesting. It's been a while since I've ingested data not from inside the worker threads themselves. So like from the host main thread, try to get the workers to do some ingestion, though I suspect we could do something fairly similar where we create this sort of channel and we just give a copy of it to, let's say, worker 0 or something like that. It's going to be gross. We're going to put like the recv into an arc mutex and have like someone take it, basically. But all that we need is someone who's able to call this now and again whenever it sees that there's data there. Well, I suppose we're trying to mock that up right now. So we have send and receive already. I guess we'll have to give different names here. And we are, so this is the send side of things. We're going to keep that ourselves. And this take side, actually what we're going to do is let take be stud sync arc new stud sync mutex new sum of take. So we need to make it be an option so that someone could go and steal this, and one person gets it, they replace it with a none. And we're going to do let take be. So everyone's going to grab a copy to this arc thing, the sort of shared reference counted pointer to the mutex, but very soon it's going to have nothing on the other end of it. And I suppose we should try to do that right away. So we're going to try to, well, I always mess up mutexes, but like we are going to, oh no, I see, sorry, this is slightly different. We want to just do a take.clone. Do we want to do take.clone? Sorry, just a moment, bear with me while I, this might be right. We'll have to see. So we come in, we've moved ownership of this arc thing into the closure. We're going to lock it, and this is going to synchronize the worker threads. We're going to, whoever wins is going to pop it open and then swap what's in here for a none. So one person should get some of the receive side of this channel, and everyone else could get none. We're only using one worker at the moment, but even if we had multiple workers, someone's going to win. If we wanted to, we could try to carefully make sure it was worker 0 or something like that, but we're not going to do that. And down here, so just before we're done, we've built our data flow. We've gone and we've inserted this nonsense in here. What we kind of want to do is hang around and just keep pulling stuff off of the take side of things. So we could do for chord in take. Forget exactly how this. I think there's like we actually want to use like a wallet something try take, but we'll look into that. This might block indefinitely if I forget what happens when we drop the other end. Like we're trying to shut down the program cleanly, for example, but we'll find out. So for x comma y in here, we're going to insert x comma y. And we might need to, so we don't have a language for unsetting a location at the moment. We could totally do that. Like we could either keep some smarts about what the current state is, or we could just have a little bit of logic that does a count first and says that if you're an even number, then you're turned off, and if you're an odd number, then you're active as a guest, so that you just keep inserting stuff and that toggles your state over and over again. Whew. So I've written a bunch of code here. I'm sure I've not connected all the dots. So the board view is going to want both a recv and a give. This is the wrong type, but we'll actually I suppose we could write in this type. So this needs to be a I64, and we don't have a lot of choice about the receive side of things. We don't get to since we did this capture stuff, we don't get to well, we could not do capture if we wanted. We do a capture down here, which is sort of built-in timeless stuff. We could totally, this is super cheesy, I don't recommend this, but in the inspect, we could totally, at this point, just push records directly into send. Maybe that's worth doing, just in the interest of not showing you all of the timely coordination stuff, which is super valuable if you want to faithfully reproduce everything that timely dataflow is seeing. But perhaps we just want to take x here. And instead of printing a thing, let's do send dot. It's either send or try send or something like that. What are we gonna send? So x that's coming in here is t and a d, so time and a diff, and also x and y. And a count. And so what we're going to want to do probably is we don't really care about the time. We could just send the whole thing, I suppose. Let's just send the whole thing because we'll possibly want some of it anyhow. So we're going to send x.clone because what we get in inspect is a reference. We don't get the actual record. And we could still probe it afterwards, though we're not really using the probe at the moment. The probe is the sort of thing that would tell us when we can stop executing, but right, so roughly right around here, for example, we might want to do something like input.advance, advance2, let's check. Oh my goodness. We want the one in input. Advance2. This is a thing that on our input session will tell the system how we're done with whatever time we were at previously. Hopefully there's a, it's not here. Time, great. So we're going to advance to basically time plus 1. And we should probably input.flush. These are relatively lightweight and don't, they can buffer information locally. Input.flush actually makes the system aware of everything that's going on. And now we do our probe E sort of thing. So while so this is the conventional timely dataflow idiom that says you've got this probe. It's at the end of your computation, and as long as the probe is still telling you that it could still be producing data strictly less than this time that you've advanced to, yeah, we should probably keep running, right? That means that there's still something at a prior time in the system it hasn't necessarily cleared, for example, this inspect, which is going to ship some data out. And if we don't do this, and we just go and maybe block on trying to grab the next record out of that source, then we maybe haven't actually done the work that we need to do. We're blocking the thread now, the worker thread, and we don't want to do that until we're sure that we've done all the work that we think we need to do. I think, to be totally honest, I think we actually want to do if let some take equals take. This was, if you recall, this is an option that only one person gets. So we sort of unpack it, make sure that we actually know that we have the channel, and then if we're the one who's responsible for it, we do all this work. Everyone else, all the other workers, will just fall through here and sort of reach the end, and when a timely worker reaches the end of its logic and doesn't have anything else to do, it hangs out basically and continues to do data flow work until the data flow is shut down. So they won't, it's not a problem that they're not also calling worker.step. They're going to just do this in a loop privately, sort of in the destructor for all this stuff. Oh boy, okay, so now, this is great. Now we have a better sense for what receiver is going to receive. So we believe it is an I size at the end, I'm hoping, an I32 just before it. And just before that there's a pair. Pair is a pair of I64, I64, and maybe an I size. So these are the X, the Y, the count, the time, sort of the round of input, and the whatever the change is that is happening to this count, right? So this is, I mean, it's totally possible, actually. I wonder if we can do this. It's possible we could finesse this to not do the count and just tell you these two numbers are a little redundant, I suppose. All right. I've written a lot of code without actually checking to see if any of this builds or not. Let's comment out this on event thing and see, at the very least, what's gone wrong. Okay, so it's just not even formatted correctly. What sorts of things? We have an unexpected delimiter at 133. It looks like I probably just screwed up something in this pile. All right. A lot of errors. So, inspect isn't closed properly. Is that right? Yeah, that looks true. Close off inspect. Down to 16 errors. Exciting. This is just utter nonsense that I should have written better. Oh, we have a bunch of these imports that we need to pull in. Let's just grab all of those. I have no clue which of these are actually important to have access to, but we're gonna want all of them. 9 errors, great. Okay, hash map not found. We should definitely add that. Line value width. That's right, because it's self.width, self.height. We don't have a new function yet. We're gonna have to add that, aren't we? Geez, I hope this is width and self.height. So let's also add a impl board view. Fun new produces a self, and it's going to need to take in these two horrible things. So state is going to be default, just an empty hash map. Recv give. Let's fix the height to be where we had it before, 35, and width of 70. And we can clearly just screw around with that if we want. We called these things different things. We called them call and row down here. Those actually sound like better names, to be honest. So column, X goes through the columns, and Y goes through the rows. Cannot find value X, okay, because we changed things, that's a good point. And down here, our send thing returns a result, and inspect wants you to return nothing. Which kind of makes sense, so I think we just want to do an unwrap there. We could, sorry, let's be slightly better and do an expect. Alright, and there's some fun stuff about default now. Yep, I can believe this doesn't have a default implementation. Who wants it to have a default implementation? Oh, we have a derived default probably that we copied. Let's delete that. Very close, all right. These folks here, we are, okay, we're gonna get some exciting converting between usize and I64 crap again. This stuff drives me wild. So, we are iterating through all of this stuff, and we would prefer that it was not, that we treated it as integers. So I think we want to do, I64. Which basically tells us that we really don't care. And this should be fine. This direction is totally fine. We might expect in the other direction to get back negative coordinates, but importantly, we're doing a clever thing here where we've populated our arbitrarily complicated state, and we're using these nice small values to sort of ask what's present in a particular region, as opposed to trying to plot everything that exists in our state somewhere on the screen. That would probably cause breaks. Oh shit, we actually need these things to be, so sorry, I guess we're going to move this nonsense into, what a so in this brief moment here, we're going to look things up. We are going to go and do our okay, getting closer. So as you move through Rust's build process, we're now close to the end where it's doing its lifetime analysis. And for example, we're here using send, but not making it clear they want to move ownership of send into the closure. Should be fine. Use of borrowed, yeah, so we both use probe in here and also outside, so we need to we can't delete the move here, but we can do, sorry, don't think we can delete the move here, but we can do so if you ever have problems with ownership, you should always be able to use move and explicitly construct the references that you wish Rust had used. In this case, we wish Rust had used a mute ref, and we're like, you should absolutely take ownership of that mute ref, do everything you need to do here. And because this closure is a fun once, at the end it expires and we can get back to just using probe without having accidentally handed ownership away. So we've got a bunch of cursive stuff that we don't use. We don't use capture anymore, so let's just comment that out in case we accidentally have to use it again. Seems totally plausible. Let's clean up some other stuff though. Required size, I don't even know what this X is. Maybe that's like a, you're offered, this is the actual size of the portal you get to try to fit into, but we're just going to ignore that. I suppose this could be handy if we weren't so demanding and we had to change our own width and height. Fields are never used. Okay, this is totally true. So at no point do we actually sort of grind through each of these things and try to pull data out of them. And that's absolutely the case. And where is a good place to do that? So the clicking is a good place to send stuff, right? We can definitely figure that out. I'll have to find a good place to receive stuff as well. We could totally do that in the clicking, just, if it makes this like a click-powered engine where if you want to see more data, you have to keep clicking. That sounds terrible. What we need to do otherwise, we could do it in draw, but what we need to do otherwise is find some way essentially to invalidate the region and say like, oh, you should just keep pulling me because I need to keep pulling off of this this little bit of whatever it is that I'm. Well, we'll put something together. No worry. So let's look at this onEvent thing and try to reason through what's going on here. So there's only one event that I particularly cared very much about, which was mouse release. And that was a thing that comes in with an offset and a position, and you can do a little bit of math here to say the offset. These are both essentially absolute. So it's like, where did the mouse actually get clicked, and where is your 0 for your window? So you do this little check sub type thing, and that's now in sort of an XY in our portal. And what we could do at this point, I think, is just self.give send .y. And we've certainly got the types wrong there. We'll just have to see what they are. And I suppose I have no idea. The example that I lifted this out of occasionally returned event consumed. Not in all cases though, so I'm not entirely sure what it signifies. But let's do that. That seems like a fun thing to do. I suppose it's important not to consume the event if it's outside of our region. I'm not sure why we got told in that case, but like, fair enough. So expected I64 found a use size. So I think that's some more try from stuff. Can make this into a maybe a slightly more pleasant looking try from blah blah. Apparently that's wasn't in the scope. All right, so that does the thing. No idea if it does anything particularly good. We haven't rigged anything to actually try to take any data out yet. What we could do, and this could be a total disaster, is in the draw logic we could try to peel off a record. Again, I'm not entirely sure. So we can peel off record at a time and sort of redraw ourselves, and I have no idea what causes this to be invalidated and run again. So, but let's just write that. And if we're at the end of the thing, like we're not receiving any more data back, we don't really want to hang everything, right? Because then we would never get another mouse event. Well, I'm pretty sure that there's, for each of these two folks, there's a non-blocking way to pull data off of it. So let's consider that at least. Just update, I suppose. Equals, what do we got? Self.recv dot, let's do try take. I have no idea. So we are going to go to Rust channel. And we're going to look on the receiver side. And we're going to look for try recv. That sounds great. Which will give us back a result, either OK of something or a certain error. And great, the errors, we don't really care. In both cases, I mean, if we want to cleanly shut down, we do one thing, but in fact, we could do while let. So our update is a whole bunch of stuff, right? There's an X and a Y and a count and a time that I don't think we care about, and a diff. So we are going to, essentially what we're looking for are these, if there's a negative thing, we want to go in and pop whatever value is present in the count and throw it away. And especially if it is this value. And if it's a +1, we want to go ahead and install the count in this location. And we're just going to write like a loosey-goosey version of this to start. So let's do the following. This is terrible, but terrible for a few reasons apparently. But oops. All right, we're not allowed to update our state in draw. Well, we could totally update our state on event. That's also pretty good because we get to sort of drive those ourselves. This has probably some weird synchronization issues though. Like before we can see the updates, we'll have to click again or something terrible like that. There's like clearly a race here that if we go and we send it some information, we're gonna need to wait some amount of time before we can actually see the results. Not one that's carefully controlled. All right, well that build, that's a little surprising. What do we think will happen if we run it? I need to get our terminal up again. So it's stuck. I'm guessing it's stuck because I think the main thread actually sort of bails right here. Not bails, sorry, but like pauses here, and we need to detach the timely worker guards. Well, let's double check that actually. I'm doing my best to try to remember. Yes, no one cares about the letter T. Keep from args, turns these worker guards, and the interesting thing that's happening is the worker guards in their drop code make sure that the computation finishes, essentially. So all that we really need to do, I think, is just capture them. So if we let guards be all of this nonsets dot expect, that is now more likely, at least, to let control flow past this point instead of dropping the stuff there and basically seizing up until the computation is complete. Hey, look at that. All right. So let's try this. Whoops. No. Let's get out of this. Let's try this in somewhere that we can actually interact with it. Oh my goodness, this is not expected to work. This is, sorry, what I've done is I've just been clicking on things, and you can sort of see that, I don't know if you can tell, but like, after I click on a thing, I gotta go do something else, and then we actually get the results out of it. Fascinating. This actually seems almost like it's working, minus all the horrible synchronization issues. Yeah. You can see some lines. Obviously, I'm curious what happens if I click on a thing. All right, so we don't currently yell at you if you actually clicked on a mine, for example. We should have, but we don't. So we could try to think that through. Also, we could also just, I mean, we have that logic for like what's a mine or not, and we could totally just put like a big red X if there's a mine. Let's do that now. That's super easy to put in, I think. So we had this logic. It's possible they want to like bundle this up somewhere, but if we are showing you a thing, right, then that means you clicked on it. So now for this to all be legit, actually this has to have the same type as we used up there, which is I64. So let's do this. Let's make an actual copy of the thing that we would have used. We can use that here as well. And we want to make this ideally, or that thing, we want to make it like bright red or something like that. So I don't know what these numbers range through. Let's try an 8. Whoops. Well, that's annoying. So we could have this come back from the data flow thing, or we could just bake into the board view the little bit of logic that we use to try to determine whether a thing is a mine or not. Let's make a little function here. And we can actually use that here as well, I think. So we steal the logic again, and we just do this, I think. And we will. So in principle, this should implement clone, I think, but probably not. I don't know if closures derive copy or not. Let's try. And we'll want to also construct the board view with this. And I've not done this before. I've not checked to see if. Oof. Yeah. Okay, that makes sense. we might have to do some explicit clones of this thing, but yeah, right. This is looking not so. Well, I guess we haven't done the ownership pass yet, but I was gonna say it's looking pretty good. Right, we gotta call this slightly differently because Rust thinks that we're trying to call an actual method as opposed to a member that happens to be a method. Cannot move out of it, so we are gonna need to clone this, or at least try to. And if we move it into here, I bet we'll just do that, and we'll let this be the second one. Let's see if that works. Hey, it does. So all that we did is just, you know, the closure is simple enough. It has a little bit of state that it does close over the denominator and the numerator. And Rust is bright enough to realize that state is clonable. Sort of the derived struct is clonable. Well, we just ran it and draw any pictures. I wonder what that's about. Wait, did we just horribly break a thing? So we made a change. I didn't think it was a very big change, but it now causes us to just exit cleanly and not do anything. And I wonder if did we fuck up the 1 and 10? Yeah. The mine testing logic to maybe cause like the computation to be vacuous. What would that cause things to exit? All right, hold on a second. Or go run. Yeah, actually ran. What did it do? Kind of hoping that it would have yelled at us if we had like crashed somewhere or done something horrible. Testing to see if it's a mine, just like we did before, and the logic's the same. What's different? Viewing data, and then some trash. See, nothing of consequence. I don't know, I wonder. I mean, it's totally possible there's some crazy race in here that we didn't hit that first time that we had that delightful interaction with everything. But it looks like oh geez, well, how did we break things? Put a little closure in there. We tried to draw that X. If we don't do this, does life go back to normal? We just made up a random thing that goes into, yeah, okay. Maybe putting an 8 in there is broken. Let's see. Let's get out of here. If we put a 3 in there instead. Yeah, okay, checks out. No, we weren't actually supposed to, yeah, good point. Okay, sorry, we did the logic a bit wrong. We don't want to do this unconditionally. That just reveals where all the mines were. So what we actually want to do is if it's in a place that we probed, then we should go and foremost print an X if it's a mine. Otherwise not. I guess that's you could toggle between those two things as a little helper mode to help folks who aren't having great luck. All right, this is back to where we were before. Let's see if I can interact with this a little bit now. Oh, we even print out received down there. That's helpful. Oof, that's less helpful, I suppose. We'll have to ditch that. But yeah, okay. Now we're back, and you can sort of see there's an X there, but it's not super bright red. I'm not really sure what colors we can use here. Let's maybe 7. Maybe these go from 0 up to 8. Oh, nope. 7's a bad number. We shouldn't use that. That causes it to bill out immediately. All new. I have no idea what all these small numbers are. Surely 4 is a good number. Suppose we can make the other one smaller, can't we? Yeah, look at that. Go on, expand out. There we go. So we can see a mine that we clicked on there, and that's too bad. Let's see. There's some other things we might. So let's trash this these error printouts because those are clearly just in the way. There's some other things we could think about doing. Like we haven't actually. No, I guess this is fine. I was gonna say we could try to write down which cells were actually the original guesses in case we wanted to undo them, for example. We haven't put the undoing logic in yet, though. That should be super easy to add. But maybe we could try it out and see if we can undo. For example, click on a mine and then undo it. So let's just do that. What that looks like, I believe, is just over here where we have guesses. It was just an input before. We're gonna do a little bit more logic with it first. So guesses. So guesses now might have a multiplicity, right? We were thinking of it as 0 or 1. So guesses when a record occurs with a count of 1. But if we let people keep inserting stuff, then we could do a count and then a filter of ignoring the coordinate, but looking at the count. It's say if the count mod 2 equals 1. And then we don't really care about the count in that case, so we just care about the chord. Sweet. And now we do our previous stuff. That still type checks, that's good. I suppose, sorry, I'm gonna clean up some of this 157. Hashable is not needed here anymore because we use that stuff. Direction, I don't know what these things are, so we're just gonna guards. I think we can underscore. I don't think that drops it. We don't want to drop the guard because that causes. So go ahead. I don't think underscore drops it. I think it just causes Rust to stop complaining. It still drops at the end of its scope. Great. All right. So here we are again, clicking on things with our delay. Here's a mine that we can click on. Here's another mine that we can click on. Another mine. And let's see if we can do this. We can go back and potentially, never mind. Say unclick on the X's though. I guess I screwed that up. So, well, it's possible. Sorry, it's possible that nothing's like the screwed up stuff is over on the deletion side, where like if that it all is just stuck in this state, then that's embarrassing. So let's so it's very possible that we're just not correctly updating our local copy of the state. I mean, lots of things can happen, but this will help us bisect where the problem actually is. No, it won't. What we'd really like to see, and this might be a little tricky with this particular interface, is what we're seeing as updates. Which is a bit awkward because well, we managed to print it on the screen before, so hopefully we can do that again and try to figure out. We're definitely seeing some positive updates, right? Because we're actually drawing the nice little pictures, but wow, okay. So we're getting, I see counts of 2. Oh, I didn't draw the, I'm sorry. I didn't draw the diff, which is actually super important. And to be honest, let's get rid of all this. There's just a lot of noise that's there that's making it hard to grok what's going on. So lots of diffs of 1, that's great. There's also a diff of 1. I have no idea where the I mean, it's possible that we're not actually returning anything at all. Like, it could be the fact that we're not seeing anything doesn't necessarily mean that we're drawing it badly. It might just be the differential is not doing what we expect. Yeah, it looks like we're not getting any diffs back, or at least under the premise that it's continuing down and to the right roughly at this point. More exciting additions to our map here aren't actually resulting in any changes, which sounds like we might have botched the logic up here. Let's take a look. Filter things, we're going to look for things who have a count mod2 equals 0. I don't know, this looks not so bad for me. Well, I'm not sure. And to be honest, I'm not sure about the right way to go and debug this right now. I mean, the graphical interface is sort of sweet, and I haven't actually thought through the right way to like put a little text display somewhere on the side to tell us things, or to dump the debugging information out the side somewhere. But I think, other than the fact that we can't seem to undo anything. Actually, just to check that we can't undo anything, let's double click in one place and then double click a second time. That's definitely not. So if we're toggling and correctly updating things in response to repeated clicks in the same place, that should sort of expand out and then vanish back again. And that's definitely not what's going on. So we'll want to look into this some more. But I think I feel like I've made a bunch of interesting progress today, and except for the fact that we're not actually waiting, for example, for the right answer before we render the screen. We're sort of one click behind always. And for the fact we don't seem to be able to undo things, which is the one thing that Differential Dataflow is supposed to be good at. I've done a bunch of fun stuff today. So I think I'm gonna call it here for now and reflect a little bit on the right way to move forward with clicking on some more of these things. Maybe what to do next about the cursive stuff. Is there more interesting set of things we could do with this? Should we be able to move the viewport around, for example? You could do like up, down, left, right, potentially slides the viewport around so that you're looking at a different part of the world. That seems utterly plausibly interesting. But yeah, we're gonna stop for now, and hopefully see you all around next time.